Hello everyone, I am Dr. Gitanjali Mehta, Associate Professor, School of Electrical, Electronics and Communication Engineering, Galgottians University. So today we are going to discuss about the steady state behaviors with sinusoidal excitation. And the topics that we are going to consider today, or we can say the objectives, are AC circuit containing resistance only, AC circuit containing pure inductance, and AC circuit containing pure capacitance only. Why sine waveform? Although it is possible to produce alternating voltages and currents with an endless variety of waveforms, for example, square waves, triangular waves, rectangular waves, etc., yet the engineers chose to adopt sine waveform because of the following advantages. The sine waveform produces the least disturbance in the electrical circuit and is the smoothest and efficient waveform. The use of sinusoidal voltages applied to appropriately designed coils results in a revolving magnetic field which has the capacity to do work. The mathematical computations connecting with alternating current work are much simpler with this waveform. Hence, because of the above advantages, electrical supply companies all over the world generate sinusoidal alternating voltages and currents. An alternating voltage may be generated by rotating a coil at constant angular velocity in a uniform magnetic field or by rotating a magnetic field at a constant angular velocity within a stationary coil. In either case, the generated voltage will be of sinusoidal waveform. The magnitude of generated voltage will depend upon the number of turns of coils, the strength of the magnetic field, and the speed of rotation. The first method is used for small AC generators, while the second method is employed for large AC generators. Now let us consider an AC circuit containing resistance only. Consider a circuit containing a pure resistance of R ohms connected across an alternating voltage source, as shown in the figure here. Let the alternating voltage be given by the equation small v that is equal to Vm sin omega t. As a result of this voltage, an alternating current I will flow in the circuit. The applied voltage has to overcome the drop in the resistance only. So V is equal to IR, I is equal to V upon R. Substituting the value of V, we get I is equal to Vm upon R sin omega t. The phase angle, the applied voltage and circuit current are in phase with each other. Coming to power, in any circuit, electrical power consumed at any instant is the product of voltage and current at that instant. In the figure, you can see the waveforms for voltage, current, and power. The instantaneous power, denoted by small letter p, is equal to product of V into I. Substituting the values of V and I, we get Vm sin omega t into Im sin omega t. Solving for this, we get Vm Im upon 2 minus Vm Im upon 2 cos 2 omega t. So this power consists of two parts, with a constant part that is Vm Im upon 2 and a fluctuating part that is Vm Im upon 2 cos 2 omega t. Since power is a scalar quantity, average power over a complete cycle is to be considered. So the power consumed, that is denoted by capital letter P, is equal to 1 upon 2 pi integration of 0 to 2 pi Vm Im upon 2 d omega t. Solving for this, it comes out to be Vm upon root 2 into Im upon root 2. That can be written as simply V, capital V into capital I. The capital letter V denotes the RMS value of the applied voltage and capital letter I denotes the RMS value of the circuit current. So average power denoted by capital letter P is equal to Vm Im upon 2, that is equal to V into I. We come across a term that is conductance denoted by capital letter G, that is the inverse of the value of resistance. So G is equal to 1 upon R. Next, moving on to AC circuit containing pure inductance, as can be seen in this circuit. When an alternating current flows through a pure inductive coil, a back EMF that is equal to L di upon dt is induced due to the inductance of the coil. The back EMF at every instant opposes the change in current through the coil. Since there is no ohmic drop, the applied voltage has to overcome the back EMF only. Applied alternating voltage is equal to back EMF. Phase angle, current lags behind the voltage by pi by 2 radians or 90 degrees. Hence, in a pure inductance, current lags the voltage by 90 degrees. This is also indicated by the phasor diagram, as shown in the figure. Inductance opposes the change in current and serves to delay the increase or decrease of current in the circuit. This causes the current to lag behind the applied voltage, as can be seen in the waveform for voltage and current here. Inductive reactance. Inductance not only causes the current to lag behind the voltage, but it also limits the magnitude of current in the circuit. So Im can be represented as Vm upon omega L, where omega L is the inductive reactance represented by XL, and that is equal to 2 pi F into L. So the figure shows the waveforms of voltage, current and power. Let the equation of the applied alternating voltage be V is equal to Vm sin omega t. This is equal to L di by dt. Now di is equal to Vm upon L sin omega t dt. Integrating both sides, we get I is equal to Vm upon L integration sin omega t dt. Simplifying this, we get Vm upon omega L sin omega t minus pi by 2. The value of I will be maximum when sin omega t minus pi by 2 is unity. So capital letter Im is equal to Vm upon omega L. Substituting the value of Vm upon omega L is equal to Im, we get the relation I is equal to Im sin omega t minus pi by 2. Now calculating the instantaneous power, P is equal to V into I, we get the relation instantaneous power as P is equal to instantaneous power P is equal to minus Vm Im upon 2 sin 2 omega t. The average power denoted by capital letter P is equal to the average of instantaneous power over one cycle. That is equal to 1 upon 2 pi integration of 0 to 2 pi minus Vm Im upon 2 sin 2 omega t d omega t, that is equal to 0. Hence the power absorbed in pure inductance is 0. Next, moving on to AC circuit containing capacitance only, as can be seen in the circuit here. When an alternating voltage is applied across the plates of a capacitor, the capacitor is charged in one direction and then in the other as the voltage reverses. The result is that electrons move to and fro around the circuit connecting the plates, thus constituting alternating current. Coming to the phase angle, it is clear that current leads the voltage by pi by 2 radians or 90 degrees. Hence, in a pure capacitance, current leads the voltage by 90 degrees. Capacitance opposes the change in voltage and serves to delay the increase or decrease of voltage across the capacitor. This causes the voltage to lag behind the current. We can see the waveforms of voltage and current in the figure here. Coming to capacitive reactance, capacitance not only causes the voltage to lag behind current, but it also limits the magnitude of current in the circuit. I can be represented by Vc upon Xc, where capacitive reactance is Xc is equal to 1 upon omega C, that is equal to 1 upon 2 pi F into C. So in the waveforms here, we can see the waveform for voltage, current and power. V is equal to Vm sin omega t. As a result of this alternating voltage, alternating current will flow through the circuit. Let at any instant I be the current and Q be the charge on the plates. Charge on capacitor Q is equal to C into V, that is equal to C Vm sin omega t. Circuit current I is equal to d upon dt into Q, that is equal to d upon dt C Vm sin omega t, that is equal to omega C Vm cos omega t. So I is equal to omega C Vm sin omega t plus pi by 2. The value of I will be maximum, that is Im, when sin omega t plus pi by 2 is unity. So Im, the maximum value, is equal to omega C Vm. Substituting the value of omega C Vm is equal to Im, in equation 2 we get I is equal to Im sin omega t plus pi by 2. Instantaneous power is given by P is equal to V into I, that is equal to Vm sin omega t into Im sin omega t plus pi by 2. That is equal to Vm Im sin omega t cos omega t. Simplifying this further, we get the instantaneous value of power as Vm Im upon 2 sine 2 omega t. Average power P is equal to average of P over one cycle. That's equal to 1 upon 2 pi integration of 0 to 2 pi Vm Im upon 2 sine 2 omega t d omega t, that is equal to 0. Hence, we can see that the power absorbed in a pure capacitance is 0. So today we have discussed about the AC circuit containing resistance only, the AC circuit containing pure inductance, and the AC circuit containing pure capacitance. So these are the references given here. Thank you.